Another way that we can graph a polar equation is with the help of symmetry. Now there's three types of symmetries that I want us to be aware of. The same three that we had in rectangular world are also in polar world. We have symmetry about the polar axis or the x-axis, where some r and theta corresponds to some r and negative theta. The second one that we have is kind of on that traditional y-axis or on the line theta equals pi halves, where we have a reflection about that axis. And then lastly, the third possible symmetry that we have is about the origin or the pole using our polar words. And you can see it reflected about, again, the pole or the origin. Now, one of the things that we got to be careful about using the symmetry test is it's a little bit tricky as compared to rectangular world. And the reason why is that if we test an equation for symmetry, which means that if we put in the alternate set of points and we get the original equation, that shows symmetry. Well, in polar world, if we do that and it comes back that we got the original equation, then we know that that equation or that graph is symmetrical about whatever one we chose. However, if it fails the symmetry test, that does not necessarily mean the graph is not symmetrical about that particular item. So we're going to look at a couple of examples of how that plays out. So again, kind of the overall idea is that we can graph using symmetry, three different symmetry tests. We'll show you some examples of how to do that. If it passes the test, then there's symmetry. If it fails the test, then there may or may not be symmetry. So let's test for symmetry on this polar equation, r equals 1 minus cosine theta. Now remember, a polar equation is an equation in terms of variables r and theta. So let's test for symmetry about the polar axis where we replace r and theta with r and negative theta. So r equals 1 minus cosine negative theta. Remember that cosine is an even function, so the cosine of negative theta is the same thing as the cosine of theta. And notice that those two equations are matching. So there is going to be symmetry about the x-axis. Now let's check for symmetry about the y-axis. Take original equation and instead insert negative r and negative theta and then work it through. Remember again, cosines are even functions. So negative r equals 1 minus cosine of theta. Solve for a positive r, so multiply everything through by a negative 1. So r is going to equal negative 1 plus cosine of theta. And I'll just rewrite those around. So it's cosine theta plus a 1 minus a 1. And that does not match up with the original equation. So there's no symmetry, or there may not be symmetry about the y-axis. Just remember, just because it fails a test doesn't necessarily mean there is a symmetry about that particular point. And our third symmetry test is about the origin. This says is let's look at where we have the negative r and a positive theta. Whoops, I had a 1 minus there. Solve that for positive r. So multiply through by a negative 1. And once again, I get the cosine of theta equals, or r equals cosine theta minus 1. So what that tells me and tells you is that we know for sure there's going to be symmetry about the polar axis. But we're not convinced that there's not going to be symmetry about the other two, about the origin or the y-axis. So let's go ahead and graph a few points here and kind of get a sense of what this graph looks like. Now to kind of close this problem out, let's go ahead and graph this knowing that we have some symmetry involved and how symmetry can help us. I went ahead and created a theta r table. I chose our typical 7 points that we begin with. Just like in XY world, we would choose maybe like 1, 0, and negative 1. In polar world, we like to choose some values that we know and are comfortable with of some exact values, and such as pi 6, pi thirds, pi halves, and so forth. And I know as we're beginning to look at these, we don't look at those and think those are comfortable. But again, with more practice, they will become more and more comfortable, and those become the primary ones that we'll use. So let's graph these points and show how symmetry can help us. So I know at an angle of 0, I have a distance of 0. On the pi 6th angle, I'm 1.3. I have these at 0.5 increments. Pi thirds in the pi thirds direction at 0.5. In the pi half direction, I'm at 1. In the 2/3 pi direction, I'm at 1.5. In the 2/3 direction, I'm at, oh, I already did that one. In the 5/6 pi direction, I'm at 1.87. And then in the pi direction, I'm at 2. So what I have now is the beginning of a circular graph in polar world here. Now we know it's symmetrical about what? It was symmetrical about the x-axis. So I don't have to plot the rest of the points around there and figure it out. I can just use symmetry to help me discover where those points are, because every point I plot has a symmetrical point about the polar axis. And then from there, continue to graph a nice smooth graph. And that's how we can use symmetry to help us graph some of these particular functions. Now remember, I said earlier that we know for sure that it's symmetrical about the polar axis, but we can't say for sure that it's not symmetrical about the other 2 points. But after reviewing the graph, we can see that the reason why it failed the test is because it failed the test. All right, let's look at another example how we can use symmetry to help us. Let's look at another example here where I have r equals 1 plus the 2 sine plus 2 sine theta. Let's check for symmetry. Let's begin by looking at the symmetry about the polar axis, where we replace theta with negative theta. Sine is an odd function. So sine of negative theta equals the same thing as negative sine of theta. And you can see that I do not get the same equation I started with, so there's no symmetry about the x-axis. Let's check for symmetry about the y-axis or the vertical axis. Replace both of them. So negative r. The right side will remain the same. We'll do the same work to it, so I'll just kind of, whoops, that was a plus there, wasn't? Got a little carried away. I know I'm using some of the work I did on the first one, so I just jumped down straight to 1 minus 2 sine theta, solve for a positive r, multiply through by a negative 1, and so then I get negative 1 and a positive, so it's 2 sine theta minus 1. And it fails that symmetry test. And let's check for symmetry on the last one, the origin. So let's put in, all right, just making sure, put in a negative r, but keep theta positive. And multiply through by a negative 1. That equals a negative 1 minus 2 cosine 0, or a minus 2 sine theta minus 1. And that also fails the symmetry test. So doing the symmetry test, each of these equations or each of the symmetry tests fails, and so it shows that there may or may not be any symmetry. So let's go ahead and start to graph it and see what we discover. So let's look at this. We know that our original graph, r equals 1 plus 2 sine theta, failed the symmetry test all across the board. Drew my template. Takes a lot of time. You guys are going to be drawing these all the time. Might be helpful to find some graph paper or some polar graph paper. I chose to go ahead and choose each of the key points all the way around, or basically I went every pi 6 of the way around and found some measures for what those are. And so I had those. So let's go ahead and start graphing those. And this is on a thing of 3, so 1 up here at a 2. So if I graph the ones in the first and second quadrant here, and I goofed up a little bit, I have a graph that starts to form like that. All right, let's graph the angles that line the third quadrant, which were right here at pi sixth. In the 4/3 direction, backwards to negative 7.3. And then if I were to graph the ones in the 4th quadrant, in the 5/3 direction, I'm backwards to negative 7.3. In the 11/6, I'm at a 0. And then 2 pi is back at 1, and it repeats itself. So I have a graph that looks like that. Now, what do you notice about this? There's two things that I think I want you to notice. One that I want you to notice is that the graph has symmetry. It's symmetrical about the vertical axis, although it failed the symmetry test. So there's a little bit of evidence or an example of where that happens. The other thing too is, what do you think that graph looks like? Does it look like a snail to you? Well, the French did, and so they have a whole family of functions that look like snails or Limacons. And they think that there's 4 types of snails that we want to become comfortable with or just be aware of. So these Limacons we have here fall into an inner loop. And notice that they're based off of these equations where I have some a plus b cosine theta sine theta or a minus b sine theta cosine theta. And all of these depend on the ratio of a to b. If the ratio of a to b is less than 1, then the graph or the Limacon will produce an inner loop. And as that ratio of a to b continues to increase such that it equals each other, then you get a cardioid or a heart-shaped graph. If the ratio between a to b is between 1 and 2, this dimple starts to show itself and becomes what we call a dimpled Limacon. And then as it gets beyond 2 and so forth, that dimple starts to disappear and it starts to flatten off. So these are 4 different types of Limacons that will pop on up as we look at some of these polar equations.